Hello, our presentation will be on arithmetic for computers. We will be dividing the explanation into 4 separate videos between me and my colleagues. My name is Joe Daher and I will be presenting the IEEE 754 floating point representation. In a von Neumann computer, all data are represented in binary numbers. These are the examples of different types of data. First, we have the integers. They are 32 or 64 bits, signed or unsigned. Memory addresses, 32 or 64 bits unsigned. Text characters and symbols, 8 bits unsigned. And finally, the real data, either 32 or 64 bits, fixed or floating point. Now I'll be talking about the ALU, or the Arithmetic and Logic Unit. The ALU is a combination digital electronic circuit that performs arithmetic and logic instructions. There are different types of ALUs depending on the types of data. First, we have the integer ALU, which is used for the integer data, a floating point unit or FPU, which is used for the real data, and finally the address generation unit, which is used to calculate addresses. This is the diagram of the ALU. The inputs are called operands, and depending on the opcode, we will obtain a specific result. There are two scientific representations, one for the decimal and one for the binary. Both representations share the same name. What I mean by that is the following. Here we have a mantissa. This is a decimal point. This is a binary point. This is the radix or the base. Here the base is 10, here it is 2. And finally we have the exponent. After many divergences because of number representations, the IEEE, which is an association for electronic and electrical engineer, standardized IEEE 754. Based on this table, there are many representations. However, we will be focusing on two, the single precision and the double precision. This is the general representation. We have a sign bit, an exponent, and a fraction. To obtain a specific number, we will be using this formula. It is minus 1 to the power sign bit times 1 plus fraction times 2 to the power exponent minus bias. This is called the significand, and it is very important to normalize. And this is called the actual exponent. We'll be talking about that later on. And the sign bit is either 0, which represents a positive number, or 1, which represents a negative number. What if we apply what was said on the previous slide on single precision and double precision? First of all, the sign bit is always 1 bit. The exponent is 8 bits, the fraction is 23 bits, and the bias is 127. For the double precision, the exponent is 11 bits, the fraction is 52 bits, and the bias is 1203. This will be clearer with the examples later on. There are some special values, and this applies for both single and double representation. The smallest and largest exponents are reserved for special values. How do we represent infinity? To represent infinity, all fraction bits should be set to 0 and all exponents should be 1. Now, depending if we want minus infinity or plus infinity, this is where the role of the sign bit will play. If it is 0, it will be plus infinity. If it is 1, it will be minus infinity. The second special value is 0. How do we represent 0? The fraction should be set to all 0, the exponent as well, and depending on the sign bit, we either have plus 0 or minus 0, which is practically the same thing. The third special value is the denormalized number. This is obtained by setting all exponent bits to 0, and the fraction is set to a non-zero value. The sign bit also plays a role to determine whether it's positive or negative. Now, finally, the fourth special value is not a number, or NaN. This happens when the exponent bits are all set to 1 and the fraction is set to a non-zero value, and this might cause errors. This is a table that summarizes all the special values that I have talked about. I will be discussing now the range of single precision. As we mentioned in the previous slide, we can't have the bits of the exponent to be all 0 or all 1. For the smallest value, the exponent should be all 0 except for the last bit to be 1. Hence, the actual exponent will be exponent minus bias, and this will give me minus 126. For the fraction part, we set all bits to 0, and this will give us a significant to be 1. Using the representation or formula we used earlier, we obtain plus or minus 1.0 times 2 to the power minus 26. Likewise, for the largest value, we set the exponent to be all 1 except for the last bit to be 0. The actual exponent will be 127. And the fraction, we will set it to all 1, and this will give me a significant approximately equal to 2. And this is the number that we will obtain. If we have a number bigger than the maximum value, overflow occurs. If we have a number smaller than the minimum value, as long as it's bigger than 0, underflow occurs. This is why we should use double precision. To find the double precision range is exactly the same idea as for the single precision. For the smallest value, the exponent should be all 0 except for the last bit. Therefore, the actual exponent will be minus 1022. As for the fraction, we set all the bits to be 0. This will give me a significant of 1 plus 0 to be 1.0. Therefore, the smallest number that we can obtain using double precision range is plus or minus 1.0 times 2 to the power minus 1022. For the largest value, we set the exponent to be all 1 except for the last bit. The actual exponent will be 1023. The fraction, we set it to be all 1. This will give me approximately 2. And the maximum value that we can get using double precision range will be plus or minus 2.0 times 2 to the power 1023. For the first example, we have to convert minus 10.75, which is a decimal number, to single precision and double precision, and finally verify our work. This is very easy and straightforward. The first step is to look at the sign. There is a minus sign, so s equal to 1. The second step is to split the number into 2 and convert to binary. 10 in binary is 1010, and 0.75 in binary is 0.11. The third step is to join both numbers. We will obtain minus 1010.11. The fourth step is to write it in this form, but first we have to normalize. To normalize this, we have to put the binary point here, so it will become 1.01011 times 2 to the power 3. Fifth step is to find the exponent. This is the actual exponent, and to have the exponent, we have to add it to the bias. The bias in the single, as we mentioned before, is 127, and for the double is 1023. We will obtain 130, which is this number in binary, and 1026, which is this number in binary. In step 6, we have to find the fraction, which is everything after the binary point. For the single, we have to extend it with 0, so its length reaches 23 bits, and for the double, till its length reaches 52 bits. Finally, we have to rewrite the whole number in the form sign, then exponent, then fraction. This is the sign, as we mentioned, because it's negative. This is the exponent that we find previously, and this is the fraction, extended 23 bits for the single and 52 bits for the double. To verify our work, we'll do the following. This is the binary single point that we obtained in the previous slide. The leftmost significant bit is 1, therefore it is a negative number. The next 8 bits represent the exponent, and the next 23 bits represent the fraction. The exponent is 10000010, which is 130. Therefore, the actual exponent will be 3. For the fraction, it is very simple. We have to multiply each of these by 2 to the power minus n, starting by minus 1. Therefore, it will be 0 times 2 to the power minus 1, 1 times 2 to the power minus 2, 1 times 2 to the power minus 4, and 1 times 2 to the power minus 5. Then, using the formula of minus 1 to the s times 1 plus fraction times 2 to the power actual exponent, we plug in the values and we will obtain the following number, same as the given. This is the last example in this presentation. This is the same procedure as before. First we look at the sign, it is 0, therefore it is positive. Then we find the actual exponent. The exponent here is 131, therefore the actual exponent will be 4. The third step is to find the fraction. As we did before, we multiply every one by 2 to the power minus the index that it has, and we will obtain 0.65625. Then, using the formula, we plug in and we will obtain the following number. Since we have to convert to hexadecimal, we take the binary number given and we split it 4 by 4 starting from the right. Using this conversion table, we will obtain the following number. Finally, it is important to know that there are some limits due to the representation of 0.10 in decimal. There is a difference between the limited precision of computer arithmetic and the unlimited precision of natural arithmetic. These are the references used in this presentation, and I thank you all for watching.